For this 2-pole 240 volt 60 hertz induction motor running at 3,470 RPM, and assuming we are studying this motor using the double field revolving theory, our task in this problem will be to calculate the forward and backward slips. Our first step is to compute the synchronous speed of this machine. The synchronous speed is a function of the applied voltage frequency and the number of machine poles, which is equal to the in actual terms 120 times 60 all over 2, or 3,600 RPM. The forward slip is the fractional speed difference between the rotating magnetic field speed n sync and the rotor speed n actual divided by the rotating magnetic field speed, which is, in real terms, 3,600 minus 3,470 divided by 3,600, the result of which is a decimal fraction 0.036. Next, we are going to calculate the backward slip, SB. In order to understand what is meant by the backward slip, SB, we have to comprehend the model that we have created with the double field revolving theory. We have three things that are going on with the rotor. First of all, the rotor itself is rotating at 3,470 RPM. In order to make this happen, the double field revolving theory tells us that there are two opposing but equal in magnitude revolving magnetic fields present in the vicinity of the rotor. The first that we are going to look at is a counterclockwise rotating field, the speed of which is directly tied to the frequency of the applied voltage and the number of poles in the machine. In this case, it is rotating at synchronous speed 3,600 RPM, which is synchronous speed and sync because it is rotating in a counterclockwise direction. We will call it an F for forward. In order to see and understand what is happening, I have obviously slowed down the speed of the rotation in our diagram, and I'm showing the rotor and the rotating field separately, whereas in reality they're rotating much faster and at the same time. However, I'm slowing things down and I'm using stop motion. It is obvious that the rotor is rotating slower than the rotating field, in this case by 130 RPM. That is the forward slip, and it is usually expressed as a fraction of the synchronous speed. In actual terms, that is 130 divided by 3,600, and that equals 0.036. The third thing that is going on is a clockwise rotating field, which we will call an R for reverse, and that is equal in magnitude to an F, but rotating in the opposite direction. So we will see that direction as minus the forward direction, or minus an F. In real terms, it is minus 3,600 RPM. We define this backward rotating phasor slip as we did with the forward slip, with the equation SB is equal to the clockwise rotating phasor speed nr minus the speed of the rotor n actual. Then we divide that again by the clockwise rotating phasor speed nr. Substituting the actual values, we get minus 3,600 minus 3,470 divided by minus 3,600, which reduces to minus 7,070 divided by minus 3,600, and that equals 1.9639. We are now going to proceed with the calculation of the backward slip as it relates to the forward slip. And that is just a series of mathematical calculations, and some of it will seem repetitive, but bear with me. I'm going to start with the forward slip SF, which is defined in terms of the forward rotating speed NF minus the actual rotating speed of the rotor divided by the speed of the forward rotating field NF. I'm going to rearrange the equation, getting rid of the fraction on the right-hand side. Next, I'm going to rearrange it to keep the actual speed of the rotor on the left and all of the other values on the right. Or in other words, I'm solving the equation for the actual speed of the rotor. And finally, collecting the like terms on the right-hand side of the equation gives us NF times the quantity 1 minus SF. Returning to our original definition of the backward rotating phasor slip SB, I'm going to replace NR with minus NF, the forward rotating phasor slip, and our equation will now look like this. I'm going to restructure this single fraction and replace it with the mathematical equivalent of two fractions, which now look like this. The fraction on the left can be replaced by 1 because the numerator is identical to the denominator. I am now going to replace the rotor speed and actual with that which we have already calculated, NF times the quantity 1 minus SF. Now, because NF is in the numerator and denominator of the right-hand fraction, we can cancel those values of NF out, leaving us with 1 plus the quantity 1 minus SF, which reduces to 2 minus SF. We have now successfully calculated the backward slip as it relates to the forward slip. And if we plug in the forward slip that we have already calculated, 0.036, and subtract it from 2, we see that it is exactly equal to that which we calculated for the backward slip, confirming the validity of our calculations. Ready to go beyond just solving problems? If you've been following my daily post and enjoying the sample problems, you're going to love this. All of these problem sets and more are now available, or soon will be, on my official course site, my Standstore for Electrical Training. Just go to the web address that you see at the bottom of this slide, https://stand.store/GVB.